Good morning students, myself Venkatesh, Department of CSE. Today we are going to discuss about a topic called as register, allocation and assignment. See, what is meant by register allocation, what is meant by register allocation and what are the various strategies for implementing register allocation. See, before going to see these topics, already we have discussed about what is a code generation. See, what are the various issues while designing a code generation, and at the same time what is a basic block and what is a flow graph. See, what is the various optimization techniques comes under basic block. That means in order to reduce the number of lines we are going to use the optimization technique. At the same time, what is a simple code generator algorithm. These all the concepts comes under code generation. You know that code generation is a last phase of compiler. It takes the intermediate code as input and finally it will give the target code as output. See here, what is a register allocation and at the same time register assignment. See, generally instructions involving register operands will take more time or faster when compared to instructions involving the memory operands. So we can say that instructions, if we use the instructions for a particular code, then only we are going to get the good efficient code. That means instead of using memory operands, we are going to use the registers for an instruction. Then only we are going to get the accurate code or good code. See here, what is the definition of register allocation? See, what is the difference between register allocation and assignment? See, register allocation means what value in a program should reside in a register. It is nothing but register allocation. It is nothing but register allocation. See here, allocation is nothing but value in a program should reside in a register. That means what is the value that are present in a register? That we can call it as a register allocation. See, whereas what is meant by register assignment? See, both are somewhat like a similar, but there is a small difference. What is meant by register assignment? So, register assignment means in which register each value should reside. That means it deals with the value, it deals with the register. Whereas register allocation deals with the value, whereas register assignment deals with the register. What is meant by register allocation? Register allocation means in which register each value should be reside. See here, we are going to, in this register allocation and assignment, we are going to use one approach called as, that approach is we are going to assign a specific value in object program to certain registers. That means in certain registers we are going to assign some specific values. This is the approach we are going to use for the register allocation at the same time register assignment. Here, by using this approach, we have one advantage as well as one disadvantage. See, what is the major advantage of by using this approach is, see here, advantage is designing of a compiler is very easy. Whereas coming to disadvantage, see what is the disadvantage? If you use this approach, we are going to use the registers inefficiently, or we are going to use the registers, too many registers we are going to use. So this is the one of the disadvantage of using this approach. See next, whereas coming to strategies of register allocation and assignment. See what are the various strategies we are going to implement for the register allocation and assignment. See here, first strategy is global register allocation. First one is global register allocation. This is the first one. And second one is register allocation for outer loops. Register allocation for outer loops. Whereas third one is a register allocation for graph coloring. Register allocation for graph color. These three are the main three strategies we are going to implement for the register allocation and assignment. See, whereas coming to global register allocation, see what is meant by global register allocation. See here, in this global register allocation, all the live variables store the variables which are in active state, all the variables should be stored at the end of each block, that is each method. See, at the same time, allocation of variable to specific registers that consist across the block, then we can call it as a global register allocation. That means the allocation should be in a block, then we can call it as a global register allocation. Next one is coming to register allocation for outer loops. See, as we know that there are loop statements of inner loop as well as outer loop, that is nested loops. See, here we are going to apply the register allocation for loops that are at the outer side. See, we are going to implement this technique for the loops also. At the same time, we are going to use the register allocation for graph coloring. See, what is a graph coloring? See, graph coloring is one of the major technique which is used for the register allocation or managing the memory. So, for graph coloring also we are going to apply the register allocation. So, these three are the major strategies for implementation of register allocation and assignment. See, next coming to one more topic, that is SDD, that is syntax directed definition. See, what is meant by SDD? SDD means syntax directed definition. See, we can say the syntax directed definition is SDD equal context free grammar along with semantic rules. Along with semantic rules. This is the definition of syntax directed definition. See, what is meant by context free grammar? See, what is the semantic rules? Here, if you see the definition, syntax directed definition means it is a combination of context free grammar along with semantic rules. See, we have a context free grammar. We are going to add some semantic rules to the context free grammar. Then we can call it as a syntax directed definition. See, what is a context free grammar? See, context free grammar is a grammar. See, what is context free grammar? See, context free grammar is a grammar which contains terminals, non-terminals, start symbol, and at the same time finally production. So this is the definition of context free grammar. That means if you take one context free grammar, in the context free grammar we are going to consider the arguments are terminals. Terminals means, as we know, terminals are capital symbols. Terminals, non-terminals, and the next one is the starting symbol, and the next one is production. So it is, then we can call it as a context free grammar. See, what is a semantic rule? Here if you see one example of SDD, that is syntax directed definition, here E produces E plus T. Here E produces E plus T. Whereas again E produces T. Here E produces T. Here this is the context free grammar. Here we are going to add the semantic rules. See, what is how we are going to write the semantic rule is here E dot val equal to E dot val plus T dot val. Here again one more thing, E dot val equal to T dot val. So this is the semantic rule. So this is the context free grammar. So here what is STD? STD is a combination of context free grammar along with semantic rules. So these two get together, we can call it as a SDD, that is syntax directed definition. If you take this syntax directed definition, what we are going to consider is, first one is context free grammar or semantic rules. See here, what is a var? See, var is nothing but, var is a attribute which is associated with a terminal symbol. It is not a non-terminal, it is a terminal symbol. Here var, what is a var? Var is a attribute, it is a attribute which is associated with a terminal, that is E. Here T dot var. So var is a attribute which is associated with a terminal T. So this is the example of syntax directed definition. See, if you see the example of one context free grammar, see, we can write the example for one context free grammar, that is expression equal to, expression produces, expression plus term. Again, the expression produces the expression minus term. See, the expression produces term. Next, term produces factor, term into factor, and term produces term division of factor, term produces factor. See, finally factor produces identifier. So this is the example of a context free grammar. See, here in this context free grammar, we have terminals and non-terminals along with the starting symbol. Here, expression produces, generally we are going to write this one as a expression produces E plus T. See, here also, the expression produces E minus T. The expression produces term. Here, term produces term into factor. Here, term produces term by factor. Here term produces, T produces F. Here F produces ID. So this is the example for context free grammar. See, whereas what are the various types of attributes in syntax directed definition? See, generally if you take the syntax directed definition, there are majorly two types of syntax directed definitions are there. Here, first one is synthesized attribute, next one is inherited attribute. See, first one is synthesized attribute, and second one is inherited attribute. See, what is meant by synthesized attribute? What is meant by inherited attribute? See, if a node take value from its children, then we can call it as a synthesized value, synthesized attribute. It means if a node takes the value from its children, generally parent take the values from its children, then we can call it as a synthesized attribute. Generally, here if you take one example, A produces B, C, D. Here A is a parent. Here A is a parent. B, C, D are the children. B, C, D are the children. Here, what is the definition of synthesis? Node that take value from its children. Here, A is a node that take value from its children. That is A dot S. It produces B dot S. Here, S is nothing but synthesized. S is nothing but synthesized. As well as we can write A dot S produces C dot S. Why? Because here A is a parent that will take the value from its children. So C is a children. Whereas next one is A dot S produces D dot S. Here D is a value, D is a children, A is a parent. So A is a node that take value from its children. So here S represents synthesized attribute. So it is the example for synthesized attribute. Next, whereas coming to inherited attribute. See, what is meant by inherited attribute? See, nothing but it is a attribute. It will take the no, if it will take the value from its either parent or sibling. Here sibling means the node which have same parent, we can call it as a sibling node. Here the node that takes value from its children. Here either it will take the value from either parent or sibling node. See here, if you take the same example, A produces BCD. A produces BCD. Here C is actually A is a parent, BCD is a children. C is a children. C dot I equal to C dot I produces A dot I. Here A is a parent. That means here C is a node. It takes value from its parent. C is a node. It takes value from parent. So value from its parent. Whereas C dot I produces B dot I. Here what is actually BCD? BCD are the siblings of A. See here, C dot I produces B dot I. That means C is a node which takes value from its sibling. Sibling B. Whereas next one is C dot I produces D dot I. Here D is also one of the sibling of C. So C is a value that takes the values from its sibling D. Here A is the parent, B, C, D are the children. Here we are going to take the values from either parent or children. So here I represents it is a inherited attribute. Here what is the major difference between synthesized and inherited is, whereas in synthesized we are going to take the values only from its children. That for that one only we are going to take left hand side as a parent only. Why? Because from parent to children only. Here, whereas inherited means it will take the particular node, take the value from its either parent or sibling. So for that one only, for the left side we are going to take one children as terminal. C dot I implies produces A dot I. Or we can say B also. B dot I produces A dot I. Why? Because B is a child. So a node that takes value from its parent. So B dot I produces A dot I. Or B dot I produces, so at the same time C dot I. Or B dot I produces D dot I. See what is here? B is a value that takes value. B is a node that takes value from its parent. Here for B is a node that takes value from its sibling. Here from its sibling. Okay. So these are all the various types of attributes that are involved in the syntax directed definition. Okay. Next, if you take one example of how to construct a parse tree for the expression 3:5 plus 4n. For this one, we are going to take the one expression grammar, that is production along with semantic rules. Here productions are there. L produces E and L. Here it means lost character, that is new line character. So E produces E plus T. In order to differentiate, here we are going to take E1. Next E produces T. Next T produces T1 star F. T produces F produces E, F produces DC. See, we are going to take this is the production. For this production, we are going to take the semantic rule means L dot value equal to E dot val, whereas E dot value equal to E1 dot val plus T1 T dot val, whereas E dot value equal to T dot val. Here value is the attribute which is the terminal. At the same time, T dot value equal to T dot val star F dot val. So T dot value equal to F dot val, whereas F dot value equal to E dot val. Finally, F dot value equal to this dot lex. So this is the production along with semantic rules. By using this production, we are going to construct the syntax tree for the 3:5 plus 4n. Initially, we are going to take the starting expression as the input. See here, the first expression is L produces En. This is the starting expression. At the same time, here E produces E plus T. Here, in order to differentiate only, we are going to take E1. No need to consider it as a E1. In order to differentiate the semantic rules, we are going to take E1 and T1. Here, what will happen? E produces E plus T. E plus T. At the same time, here E produces T. E produces T. At the same time, T produces T star F. T produces T star F. And then next we have one production called T produces F. So T produces F. See, finally we have one production called F produces digit. Or we can say the semantic rule for digit is digit dot lex. So what is the value? That is 3. Next, coming to T star F, here F produces digit. That is a digit dot lex. That the value is 5. That is 3 star 5. Next one is here, if you take E produces E plus T, here we know we have one production called T produces F. T produces F. See, one more production is F produces digit dot digit. The semantic rule is digit dot lex. So what is the value? That is 4. That means 3 star. So 3 star again 5. So up to now 3 star 5 plus 4. That is, what is our expression? 3 star 5 plus 4. And finally, what is the leaf node? That is n. So 3 star 5 plus 4n. So this is the corresponding. We are going to take one desktop calculator as an example. That means we are going to take the production rules along with the semantic production values along with semantic rules. By using the production and the semantic rules, we are going to construct the syntax tree for this one. So by using after constructing the syntax tree, we are going to reconstruct the syntax tree as annotated parse tree. See, annotated parse tree. So what is meant by annotated parse tree? See, annotated parse tree means it is a parse tree in which all leaf node will have the value. That means here we don't have anything except the values. If we are going to construct this one as a annotated parse tree, in that annotated parse tree we are going to get all leaf nodes as only values. We are not going to take anything. Okay, we are going to take all the leaf nodes as values. So this is the syntax. By using the syntax directed definition, we are going to construct the parse tree. Okay. So this is regarding syntax directed definition. Okay. Okay. Please, thank you very much. Please subscribe DBS Talks. Thank you.